Okay, so in the last video we went over just the basic sort of arithmetic or algebra for complex numbers. So you've got these pairs of real numbers like a and b, and you can add them. You can add two of them to dots in the plane, and you can also multiply dots in the plane. And when you do so, you will get another dot in the plane. Some horizontal coordinate plus some vertical coordinate times I. Horizontal coordinate plus vertical coordinate times I. And we worked out what you would get. And similarly for dividing, right? So you can multiply and add and divide. So this will also end up being something plus I times something. And we gave names to these parts. They're called the real part and the imaginary part. Okay, so that was just a recap of last time. Now I want to upgrade what we allow for functions. So we've been using x of t always as standing for a real number, because we want it to be the state of a system for which the state can be described by one real number. But now I'm going to say sometimes it's okay for x of t to be a complex number. Okay, now when I say complex number, I mean complex valued function. So complex number is a bad way of putting it. I mean, instead of having x of t be a function where you input a real time and you get out a real x, it is a function where you input still a real time, but a complex x can come out. So sometimes it's okay for it to be a complex valued function. We still, in the end, when we're solving differential equations, typically we will want real valued functions to come out. But sometimes in the middle of our analysis, in some intermediate steps, we will allow complex valued functions. Why? Well, you saw partly why, because they seem to come up naturally when we want a general solution to a second order linear homogeneous differential equation with constant coefficients. We get complex roots sometimes, and so if we can still make sense of what's going on when there are complex roots, then that would be nice. But at the end, we still want a real solution. Okay, so sometimes it's okay for x to be a complex valued function. Now, for a complex valued function, it's really made out of a real function plus another real function times I. So just like a complex number is real number plus real number times I, just like a complex number is made out of a real part and an imaginary part, a complex valued function is made out of a real valued function. Let's call it x sub real plus I times, and I think I was writing it like this, plus another real valued function, let's call it x sub imaginary, times I. So this is a little bit confusing. Again, x sub real is a real valued function. X sub imaginary is still an it's still a real valued function. So these are both real valued. Just because it's called x sub imaginary doesn't mean it's not real valued. It's called x sub imaginary because it's the imaginary part of x of t. So, example. You could have x of t equals t squared plus t cubed times I. That would be, so here's a real valued function. Let's call it x sub real of t. And here's another real valued function, x sub imaginary of t. One is t squared and one is t cubed. And if you want to plot them, then you have to plot them individually, right? Like they're actually two functions. So when I say complex valued function, it's kind of like I'm saying two functions. It's just two functions. So here's one of them that I've plotted, t squared. This is a plot of the real part of x. And then if I want to plot another one, let's put them both on the same picture, then that's a totally different plot, right? So there's parabola t squared, and then there's a cubic t cubed. So a complex valued function is literally two functions. It's two real valued functions. But we visualize complex numbers as, what they are is they're two real numbers. A complex number is two real numbers. So we visualize complex numbers as points in the plane. So if you want to fully visualize the information contained in x of t equals point in the plane, you need to visualize a function that takes values in the plane rather than taking values that are just real numbers. So there is a way of doing that, but it's a little bit inferior to... Okay, so one way of doing it is to come up with one axis for t. So in the plots that I've been showing you like one axis for time and then another axis for x sub real. So that was the plot that has the parabola. And then I was like, okay, one axis for time and one axis for x sub imaginary. Then that showed you the cubic. But if you really want to see everything all at once, rather than looking at one at a time, you would have to introduce a third axis, right? So time, real, and also imaginary. You would want to introduce all of the axes like this, so it would be like a 3D kind of plot, which you can do like this. It would look something like this for this particular example, and that would contain all the information. So one of these axes is time, and the other two are the real and imaginary parts of x. But actually what we more commonly do, since we're thinking of t as literally time, we can make things a little bit easier on ourselves if we instead of drawing a 3D plot, we draw an animation. So instead we don't waste an entire axis on t. We only make a real part of x-axis and an imaginary part of x-axis, and then we let t literally stand for time. We let it literally be time in our plot representation of what's going on, meaning we animate. So at a particular value of t, you're going to get x of that value of t equals some point in the plane, right? Real part and imaginary part. So this would be the complex plane. And for this particular example, let's see what it looks like. Okay, here's some code that's supposed to show me a point located at t squared t cubed for the real part, for the horizontal component and for the vertical component, but it doesn't know what t is, so I need to tell it. Let's just try t equals 0, and then it gives me a dot. Okay, well what if I change t, like t equals 0.2? It still gives me a dot that looks like it's in the center, because I'm not showing any axes, so it's just recentering the image. Okay, that's better. Now I'm forcing it to show axes, and as I change the value of t, the dot moves around, except it's still always centered. I'm just seeing the axes move around. Okay. There, now the axes are fixed in place, so as I change t, t is 0, the dot is 0 at the origin, 0, 0. That's because 0 squared plus 0 cubed I is 0 plus 0 I. And if I put t equals 1, then I get a dot way over here at 1, 1. That's because 1 squared plus 1 cubed I is 1 plus I, and this is where 1 plus I is in the complex plane. Now, animation means show me all of the stuff that's going on, but with t running from, say, -1 to 1. So the same range that you saw in these individual plots here, t running from -1 to 1. Except don't confuse what you're seeing in these plots with what you're about to see here. Up here, the horizontal axis was time, and the vertical axis was playing two possible roles, either the role of the real part in the case of one graph, or the role of the imaginary part in the case of another graph. Here, on the other hand, what we're going to see here, on the other hand, is time, literal time, like this animation time, playing the role of time, and the axes playing the role of only the real and imaginary parts. So this is the complex plane. This is a dot in the complex plane, and as we change time, the dot moves around. And you can see it's doing some cool stuff. So there's time 0. I'm letting time run from -1 to 1. So in the middle is time 0. That's when it's at the origin. And then as time goes to 1, then it's there. Now, that's nice that you can see the animation, and it's a really solid, good way to visualize what's going on. But what you might like to see instead is the trajectory that the dot is following. That would be a good way to visualize the information that's contained in this complex valued function. So to do that, you can parametric plot. I mean, that's what this is basically, is a pair of parametric functions. So parametric plot t squared t cubed, with t running from -1 to 1. And let me show the axes in the same range. So it's the same, it's -1 to 1, -1 to 1. And there, that's the trajectory that the dot is following. So that trajectory that you're seeing there is t squared equals t cubed. And actually, I think I can just show this in the same picture with the animation, which would be nice. No. Maybe I need to put it here. Maybe I should not make a plot range demand on it also, since I make that outside. Yeah, there. So you can see it going along. So that's pretty nice. You can think of the parametric plot as sort of summarizing what's going on. It does not contain all the information contained in the parametric function. So, for example, if you look at the animation, you can see the dot moves very quickly sometimes, and sometimes it moves very slowly, right? Look, it's slow and now it's quick. That kind of information is missing from if you look at just this picture. Then that information moving slowly versus quickly would be totally missing. So this is only showing you the trajectory. Now, you can actually do calculus with these functions. So the main aspect that we are going to focus on in this course is that you can differentiate them. And it's as simple as can be. So if you take x of t, which is maybe x real part of t plus x imaginary part of t times I, then its derivative, d dt of x of t, is the simplest thing you can imagine. It's going to be take the derivative of the real part plus, and then take the derivative of the imaginary part. And that's it. So for example, back here, the derivative of this would be 2t plus 3t squared I. That's it. So the derivative of a complex valued function is going to be some other complex valued function.